Okay, this is Math 131, section 2.6a. So the first thing we're talking about is infinite sets in this section. Infinite set is a set that can be placed in a one-to-one correspondence with a proper subset of itself. Now that's kind of might seem a little abstract, but basically you take a set A, whatever it is, and you take away one item. So take set A and then take away one item. From A. And then we see, and we call it set B or whatever. Okay. And then we want to look at a one-to-one correspondence between B and A. Okay. And that's how we can show that A is an infinite set. Okay. So if A is an infinite set, then you can take away one item from A, call it B, and then do a one-to-one correspondence with B and A. And if you can do that, then A is an infinite set. So we'll talk about one-to-one correspondence in a minute. Okay, let's look at an example first. Look at the set of natural numbers, 1, 2, 3, 4, 5, etc. Okay, now n means that the numbers continue, and then we can call n some number that's really big. Okay, but that means the numbers keep going. Okay, so we want to show that the set of natural numbers is an infinite set. So what we'll do is we'll take that set 1, 2, 3, 4, 5, etc., and just take one out. Okay. So if you take one away, okay, and then call it P, for example, now our set P is 2, 3, 4, 5, 6. Now when we get to n, okay, here, let's say this is our nth element, okay, whatever n is. Let's say it's our 50th element, okay. Now here that would be 50, but here it's 50 plus 1. It's 51 because we took away the 1 and we start with 2 here. So, 5 corresponds to 6 here, right? 4 corresponds to 5 here. 3 corresponds to 4. 2 corresponds to 3. 1 corresponds to 2. And then for the n, whatever element n is, it's going to correspond to n plus 1, which is 1 more. And the reason is because we're starting with... Okay, so we've shown that the set of counting numbers n is infinite because we show the one-to-one correspondence between n and a proper subset of that called P. Okay, and you can see that 1 corresponds to 2, 2 corresponds to 3, 3 corresponds to 4, etc. And the nth element of n corresponds to element n to n plus 1 for P. Okay, so let's say this is 30, this is 31. Okay. So that's how we show our one-to-one correspondence, is that we show the first handful and then we show element n for this small n for this set, pointing to whatever the element would be for this set. Okay, the next thing we're going to show is this set. It is called capital M, but it's not the natural numbers. It's the set 4, 8, 12, 16. Now these are multiples of 4, right? 4 times 1 is 4. 4 times 2 is 8. 4 times 12 is 6. 4 times 3 is 12, 4 times 4 is 16, etc. The next one would be 20, right? And then we can show what happens when you use a number n, where let's say n is 10, okay? That would be 40, okay? So it's a multiple of 4, so we can use 4n as our kind of our general term for this set. Right? So our given set is 4, 8, 12, 16, 20, okay? Our proper subset, we're going to get rid of the 4. So this set is going to start with 8. It's going to go 8, 12, 16, 20, 24. Okay? So it's easy to show the first handful how they correspond to each other. Here 4 corresponds to 8, the first elements. 8 corresponds to 12, the second elements. 12 to 16, the third. 16 to 20, the fourth. 20 to 24, the fifth. Now the general term of this set is a little bit more tricky. Think about 4n is, let's say, we say the nth term, like the 11th term would be n, 4 times 11, which would be 44. But here we have to add 4 because notice we're adding 4 to these, right? Because we took away the 4 and we started with 8 on this one. So if, let's say we're looking at term 11, where little n is 11, okay, then this would be 44, okay, and this one would be 48. So if we look at examples for little n, we can see what happens. we're taking 4 times n for this one, and we're taking 4 times n plus 4 for this one because we need 48. It's going up by 4 because we dropped the 4. Okay, so we're showing a one-to-one correspondence with this proper subset, which is we took the given set and took the 4 out. And when you do that, you're showing that the set that we're given, the original set, is infinite. Okay, this is a little bit more abstract concept, but we say a set is countable if it is finite or can be placed in a one-to-one correspondence with a set of counting numbers. Okay. So if you can place any set, first of all, if it's finite, like 1, 2, 3, 4, 5 is finite, that's countable. But you can also use sets that can be placed in a one-to-one correspondence with a set of counting numbers. Now our set of counting numbers we know is this, right? N equals 1, 2, 3, 4, etc. And we can have an n there, but it keeps going, right? Okay. That's our set of counting numbers. So what we can say is that all infinite sets that can be placed into one-to-one correspondence with a set of counting numbers is considered finite, okay? Because we're taking a set that can be placed in correspondence with a set of counting numbers. So we could say 2, 4, 6, 8, 10, etc. That set is called a countable set because we can place it one-to-one with a set of counting numbers. In fact, the set of counting numbers is finite because it can be placed in a one-to-one correspondence with a set of counting numbers. It's the same set, right? Okay. All right. The next concept here is that all infinite sets that can be placed in a one-to-one correspondence with a set of counting numbers have this cardinal number. Now, we would think it to be infinite, but we call it Aleph null. Okay, and we use this symbol, kind of x0, and I'll kind of write it on the board, sort of like this, because I'm not very good at drawing that, but it might look something like this on the board. Okay, so we kind of write it like that. But we could say, how many elements does this set have? Well, it's not infinite, really. It's sort of, we give it the symbol, we call it Aleph null. So that's an infinite set. It can be placed in a one-to-one correspondent with a set of counting numbers, and it has this cardinal number, okay, Aleph null, this x0, kind of. It's like a cursive capital X, sort of. Okay, so any set that can be placed in a one-to-one correspondence with a set of counting numbers has cardinal number Aleph null and is infinite and is countable. Okay, so if you can take a set and place it in a one-to-one correspondence with our capital N, the set of counting numbers, then we say it has this cardinal number, Aleph null, and it's infinite and it's countable. Okay, so we in math we say that that set is countably infinite. Okay, in other words, the set keeps going, but you can count how many elements are in it. Okay, and you can count how many elements by seeing how far you went and see how many you have. So the set does keep going, but it is countable. Okay, for first thing we're going to show for that is that we're going to look at the set of odd counting numbers and say that it has cardinality of Aleph null, or it has the cardinal number that we can say the cardinal number of that is Aleph null. So we're going to show that it's infinite and countable. In other words, we're going to show one-to-one correspondence with a set of natural numbers. Okay, so these arrows are a little bit off, but I added a couple here. Okay, so our set of odd counting numbers is 1, 3, 5, 7, 9. Okay, and we can go, so 1 corresponds to 1, 2 corresponds to 3, we're doing a one-to-one correspondence, 3 corresponds to 5, 4 corresponds to 7, 5 corresponds to 9, and then n would be the nth element in this set. So let's say n is, well, let's pick an easy one to kind of figure out what happens. Okay, so this is when n is 5, right? And it's going to give us 9 for the odd numbers, right? Because we go 1, 3, 5, 7, 9 is the 5th element. Okay, so the 6th element we know here is going to be 6, right? And then here it's going to be 11, okay? So kind of think of what happens as we go from 5 to 9, 4 to 7, and 3 to 5, and 2 to 3. What we're doing is we're doubling this and subtracting 1, right? 5 times 2 is 10, minus 1 is 9. 4 times 2 is 8, minus 1 is 7. 3 times 2 is 6, minus 5 is 1. 2 times 2 is 4, minus 1 is 3. And sorry, 2 times 3 is 6 minus 1 is 5. And 2 times 1 is 2 minus 1 is 1. So we kind of notice a pattern how we get from here to here, okay? So we can say in general, if our term is n, let's say n is, whatever, 20, okay? Then we double it and subtract 1. So the one that corresponded to 20 would be 20 times 2 minus 1, which would be 39. 20 times 2 is 40 minus 1 is 39. So we have to show a one-to-one correspondence with our general terms too. So that's the tricky part, is we have to do that. And that's how we show that one-to-one correspondence. So this kind of says, okay, for any term you can do this. If this one's n, this one's 2n minus 1. We double it and subtract 1. So we have to look for patterns to find that, usually. Okay, again I added the arrows. So we see, since there is a one-to-one correspondence, the odd counting numbers have cardinality, aleph null. That is the number of elements of set O, which is the odd numbers. That's not 0, that's the O for the set of odd numbers. Is that aleph null, okay? So we can also say this. We can show one-to-one correspondence as n with n, right? Like if we have n equals 1, 2, 3, ... n, right? And it keeps going. I should put the dots keep going. And we do the other set one as n, right? Okay, 2, 3, n. Okay, and we can say, okay, this has one-to-one correspondence. This one goes to 1, 2 goes to 2, 3 goes to 3, and n goes to n. So what we've done is show a one-to-one correspondence with n on n. Okay, that natural numbers with natural numbers. So that tells us this, that the cardinal number of the set of natural numbers is also that aleph null, because we showed that it's infinite and countable because it has a one-to-one correspondence with the set of natural numbers. The set of natural numbers does. This one shows that the cardinal number for set O is also that aleph null. Remember, these are the same. Okay. Now, aleph null is not really a number. It's sort of like infinity, but not exactly. So we kind of just say, yes, you can count. It's countable. Okay, this set is countable, even though it's infinite. So, and what's the cardinal number of that set? Well, it's this aleph null thing. Okay, we'll explain this a little more in class. I know this is kind of an abstract concept.